Einstein was at first dismissive of this. He thought it was just like, oh, the mathematicians are over formalizing again. But then he later realized
the fusion of quantum mechanics and Einstein's theories of relativity has profoundly shaped the modern world. Now, quantum computers are revolutionizing our understanding of black holes, enigmatic cosmic giants that have puzzled physicists for decades. These regions, where gravity is so intense that even light cannot escape, were once considered inescapable voids. However, groundbreaking advances in quantum computing are enabling scientists to probe black holes like never before, reshaping the fundamental laws of physics. For years, black holes were thought to be one-way traps. Anything crossing the event horizon, whether matter, light, or time, was believed lost forever. Yet quantum mechanics suggests otherwise. Information, the very essence of reality, cannot simply disappear. This paradox has confounded physicists for over 50 years. Now, quantum computers are helping solve this puzzle. The journey begins with a revolutionary concept called holography, which proposes that black holes might not be three-dimensional objects as they seem but rather two-dimensional surfaces that encode all information, like cosmic hard drives. This bold idea, known as the holographic principle, implies that everything within a black hole is mapped onto its surface. Proving this, however, demanded computational power far beyond the capabilities of classical computers. Using quantum computers, researchers have simulated microscopic black holes and tracked the dynamics of information in unprecedented ways. Astonishingly, rather than merely swallowing information, black holes seem to scramble it, and eventually release it, resolving the long-standing information paradox. This breakthrough is just the beginning. For years, physicists have grappled with two seemingly incompatible frameworks: general relativity, which describes gravity on cosmic scales, and quantum mechanics, which governs the subatomic realm. Black holes stand at the crossroads of these theories, forming through the gravitational collapse of massive stars yet behaving in ways that defy classical physics, dominated by quantum effects. General relativity predicts that black holes contain singularities, points of infinite density where the laws of physics break down. But quantum mechanics maintains that information cannot be destroyed. If information were to fall into a singularity and vanish, it would violate a core principle of quantum theory, unitarity. This conundrum is known as the infamous black hole information paradox. Theoretical models, such as Hawking radiation, suggest that black holes gradually evaporate over time, emitting energy into space. But where does the information go? Is it truly lost, or does it somehow survive? Classical computers lack the capacity to explore these questions fully. The complexity of modeling black hole evaporation involves billions of interacting quantum states. Quantum computers, however, are game changers. Unlike classical systems that process data in binary, ones and zeros, quantum computers leverage qubits, which can exist in superpositions of multiple states simultaneously. By harnessing this extraordinary computational power, scientists are unraveling mysteries at the intersection of gravity and quantum physics, paving the way for a deeper understanding of the universe. Quantum computers are unlocking mysteries once thought unsolvable, tackling problems that would take classical machines longer than the universe's lifespan to compute. Recent advancements in quantum computing have enabled researchers to simulate small-scale black hole analogs, yielding extraordinary insights. These simulations suggest that information falling into a black hole isn't lost forever but instead becomes scrambled and encoded within Hawking radiation, hinting at a potential resolution to the long-standing information paradox. Institutions like Caltech and MIT have made groundbreaking progress using quantum circuits to model information flow within black holes. By entangling qubits and simulating quantum gravity, scientists have demonstrated how information might escape from an evaporating black hole. These findings suggest that black holes may function like quantum computers themselves, processing and storing information in ways once unimaginable. The implications of this research go beyond black holes. If information isn't destroyed within them, our understanding of space-time must be reevaluated. Reality itself may be deeply quantum in nature, with space and time emerging from fundamental information processes. One of the most fascinating applications of quantum computing in black hole research involves the study of wormholes, hypothetical tunnels connecting distant parts of the universe. Recent quantum simulations propose that entangled black holes could behave like wormholes, allowing instantaneous information transfer between them. This offers potential evidence of quantum teleportation on a cosmic scale. The famous ER equals EPR conjecture, proposed by physicists Juan Meldacena and Leonard Susskind, suggests a profound connection between wormholes, Einstein-Rosen bridges, and quantum entanglement, Einstein-Podolsky-Rosen pairs. If true, quantum computers are not just tools for simulating black holes but windows into the fundamental structure of reality itself. Early experiments using quantum circuits designed to mimic the entanglement patterns of black holes have observed behaviors consistent with wormhole-like information transfer. While these findings are preliminary, they hint at the possibility that black holes may not be simple one-way traps but gateways to deeper quantum realities. This raises a profound question. If information isn't destroyed in black holes but instead transformed and released, could it one day be possible to reconstruct what falls into them? Some physicists believe that future quantum computers will be powerful enough to decode the information encoded in Hawking radiation, potentially revealing the contents of black holes. Such a breakthrough could unlock secrets about the origins of the universe, the nature of time, and even the possibility of multiverses. Thanks to quantum computing, black holes are no longer merely cosmic enigmas. They are becoming laboratories for studying the ultimate laws of physics. The discovery of Hawking radiation in the 1970s raised fundamental questions about black holes. Now, in the 21st century, quantum simulations are revolutionizing our ability to model their complex behavior. Unlike traditional supercomputers, which struggle with the overwhelming complexity of quantum gravity, quantum computers leverage superposition and entanglement to process information differently. Recent experiments at institutions like MIT, Stanford, and Google's Quantum AI Lab have successfully used quantum processors to simulate black hole dynamics and explore theories once considered purely speculative. In a remarkable 2022 experiment, physicists used a quantum processor to simulate a microscopic wormhole, not a literal tunnel through spacetime but a mathematical model that mimicked its information dynamics. These groundbreaking efforts mark the dawn of a new era in black hole physics. As quantum computing continues to evolve, black holes may reveal answers to questions that have perplexed physicists for over a century. What began as theoretical speculation in Einstein's general theory of relativity is now becoming a practical frontier for scientific discovery. We stand on the brink of unlocking the ultimate secrets of reality itself. The quantum revolution in black hole science. For centuries, black holes have represented the greatest paradoxes in physics, warping space and time so intensely that nothing, matter, radiation, or even light, can escape their grasp. However, a powerful new tool has emerged: quantum computers. Operating under the principles of quantum mechanics, which govern the fundamental fabric of reality, these machines allow scientists to probe the mysteries of black holes in ways previously thought impossible. Quantum computers possess a unique capability. They can process and simulate quantum systems in ways that traditional computers cannot. While a classical supercomputer might take billions of years to simulate the intricate interactions within a black hole, a quantum computer can achieve this in mere minutes. As these machines grow more powerful, they enable physicists to conduct virtual experiments on black holes, testing theories that have long remained confined to theoretical models. How quantum computing simulates black holes. At the core of quantum computing lies the principle of superposition, which allows quantum bits, qubits, to exist in multiple states simultaneously. Unlike classical bits, which can be either a 0 or a 1, qubits can be both at the same time, making them capable of performing extraordinarily complex calculations beyond the reach of classical computers. This capability is particularly useful in addressing one of physics' greatest challenges: simulating quantum gravity. Einstein's general relativity describes black holes on a large scale, but these equations break down when examining the microscopic structure of spacetime at a black hole's singularity. Here, quantum mechanics takes over. Using quantum computers, scientists have successfully created models of miniature black holes that behave just as real black holes should, but at a manageable scale, allowing for controlled study. These simulations help researchers explore quantum entanglement within black holes, shedding light on how information flows in and out of them. Solving the information paradox. One of the most significant breakthroughs in black hole research comes from quantum simulations addressing the black hole information paradox. Traditionally, it was believed that anything falling into a black hole was lost forever. However, quantum mechanics asserts that information cannot simply vanish from the universe. Quantum computers have offered fresh insight into this paradox. By modeling black holes using qubits, researchers have found that information may not be lost but merely scrambled. Instead of being erased, data appears to be distributed across the black hole's event horizon and encoded within the radiation it emits. In theory, a sufficiently advanced quantum computer could decode this information and reconstruct what had fallen into the black hole. This concept aligns with quantum entanglement, which suggests that particles inside and outside a black hole remain fundamentally connected. If this is correct, black holes do not destroy information, they transform it in ways we are only beginning to grasp. Black holes as cosmic computers. As quantum computing advances, an even more profound idea has emerged: what if black holes themselves function as quantum computers? Some physicists, including Leonard Susskind, have proposed that black holes may be the universe's most powerful information processors. According to this theory, black holes act as rapid scramblers, converting any matter or energy that enters them into highly complex quantum states. Rather than being simple voids that erase data, black holes could be vast quantum systems encoding everything they consume. Fully understanding how black holes process information could transform our understanding of computation and reality itself. Some researchers even speculate that insights from black hole physics could inspire new, more advanced forms of quantum computing. The holographic principle and black hole simulations. Another major breakthrough in black hole research stems from the holographic principle, a radical idea suggesting that everything inside a black hole, including space and time, might be encoded on its two-dimensional surface. Rooted in string theory, this principle proposes that a black hole's three-dimensional interior is actually a projection of quantum information stored on its surface. Quantum computers have allowed scientists to test this theory by simulating quantum systems that follow the rules of the holographic principle. These studies suggest that black holes might not truly be three-dimensional objects but rather two-dimensional surfaces encoding vast amounts of information, much like a hologram. Astonishingly, if this principle holds, it could imply that the entire universe itself is fundamentally holographic, meaning our perceived three-dimensional reality may merely be a projection of deeper quantum processes. Black holes, wormholes, and quantum entanglement. One of the most exciting developments in black hole physics is the connection between black holes and wormholes, hypothetical tunnels through spacetime that could link distant regions of the universe. Long considered purely theoretical, recent quantum computing simulations suggest that entangled black holes might actually behave like wormholes. In other words, if two black holes are quantum entangled, information, or even matter, might be able to traverse between them instantaneously. This concept, known as the ER=EPR conjecture, proposes that wormholes and quantum entanglement are fundamentally the same phenomenon. If true, it would mean black holes are not just cosmic prisons but potential gateways to other realms of spacetime. Quantum computers are actively being used to test this hypothesis by simulating entangled black holes and analyzing how information behaves within them. If further evidence supports the ER=EPR connection, it could indicate that wormholes are not mere science fiction but an intrinsic feature of the universe itself. The future of black hole research. With every advancement in quantum computing, our understanding of black holes deepens. In the next decade, scientists aim to develop even more powerful quantum processors capable of simulating the full-scale dynamics of black holes. Some of the key questions they hope to answer include: can we fully decode the information stored in Hawking radiation? Do black holes truly function as quantum computers? Can quantum simulations provide a clear picture of what happens at a black hole's singularity? Are wormholes real, And could they be used for space travel? The answers to these questions could revolutionize not only our knowledge of black holes but also our fundamental understanding of the universe. If quantum computing continues its rapid advancement, it is entirely possible that we will achieve definitive answers within our lifetimes. A universe built on information. Perhaps the most profound implication of these discoveries is what they reveal about the nature of reality itself. If black holes function as information processors, then so might the universe as a whole. If quantum entanglement shapes space-time's structure, then reality may not be composed of mere matter or energy but of pure information. This perspective aligns with a growing school of thought in theoretical physics that suggests the universe is fundamentally computational. In this view, everything we perceive, space, time, matter, and even consciousness, emerges from deep quantum processes, functioning like a vast cosmic quantum computer. If true, black holes are not just celestial enigmas. They hold the key to unlocking the deepest truths about existence itself. And with the power of quantum computing, we may finally be on the verge of understanding them.